Assalamu alaikum warahmatullah. So today is our lecture 4, and today's lecture is about the permutation matrix, permutation and inverse matrices. So permutation matrices are used for exchanging rows. So in the previous class or previous lecture, I told you about a concept that whenever you will get a 0 in the pivot position, you need to exchange the rows, right? So in case of or to change or to exchange the rows, you need to use the permutation matrices, right? So suppose you have a matrix A, B, C, D. So you want to exchange rows of this matrix, and the transform matrix would be C, D, A, B. So what operation can help you do this, or what matrix can help you do this? So this is our matrix A, B, C, D, and you need to multiply with some matrix, right? You need to multiply with a matrix such that the rows of this matrix is exchanged. So it will have a picture like this. So in which position should I multiply, here or here? So in the previous class we know that if you want to multiply, or sorry, if you want to do some row operation, we'll have to do the multiplication at the left side, okay? And if you want to do some column operation, you'll have to multiply this matrix, or the multiplicand should be at the right side, right? So if you have forgot this concept, please refer to the previous lecture. All right, so there should be something here that should enable me to do this operation, okay? So there should be some matrix here, so that if I multiply that matrix with this matrix, it will make some change or some transformation. The transformation in this case is the row operation, and you'll have exchanged rows like this, right? Now what matrix should be able to do that? So to do that, do the same operation on an identity matrix 1 0 0 1. Suppose you want to exchange the rows of this identity matrix. So 1, so it should be, the second row should be the first one, and the first row becomes the second one. Now there should be something here, something here. So there are 2 rows in this matrix as well. There are 2 rows here, sorry. There are 2 rows here, and as you can see, to do this row operation, so the result here, the result you can see here is none of the first row and ones of the second row. So we'll have a matrix here that takes none of the first row and ones of the second row, right? So if you multiply, if you do the vector matrix multiplication, what this row does, what this entry does is it takes none of the first row and ones of the second row, so that you get this output. Now the second row is ones of the first row and none of the second row. So similarly, you take ones of the first row and none of the second row, right? So if you multiply this row with this matrix, you will get this output, right? The same thing, the same logic can be applied here. The same logic can be applied here, that is, if you can see here, so this is the second row and no part of the first row is taken here, so you should have one entry that takes none of the first row and ones of the second row. Similarly, for the second row of output, you will have to take ones of the first row and none of the second row, right? Now if you just do the multiplication, you will see that you will get this matrix. Okay. What if you work with a 3 by 3 matrix? Let's say you have this 1 2 3, then 4 5 6, then let's say 9 10 11. So from this matrix you want to get this one, 9 10 11 4 5 6 1 2 3. So as you can see, the third row, the first row has become the third one and the third row has become the first one. So what matrix would do that thing? So for the first one, the first row, you take none of the first row, none of the second row, ones of the third row, then you will get this output. For the second one, the second row stays the same, right? So for the second row, the output stays the same, so you take none of the first row, ones of the second row, none of the third row. And for the third one, you take ones of the first row and none of the other two rows, right? So this matrix, that this matrix here and this matrix here, that have done the row exchanging operations are called the permutation matrix. Okay. Now a small question is, if I want to exchange the columns, let's say from this matrix I want to get this one, B D A C. So what is the change here? The change is your second column has become the first one and transformed into the first one, and the first column has become the second one, right? So this is the output. So what should be put here? What should be the permutation matrix here that would do this operation? The answer is, the approach is wrong, because we are not doing any row operation here. As we are doing a column operation, we will have to use the matrix here. Okay, so in that case, A B C D, there should be a matrix here that would do, or that would give me this output, right? So So what should be the output here? So you take, so for the first column you take none of the first column and ones of the second column. So none of the first column and ones of the second column. For the second column you take ones of the first column, none of the second column. So this should be the permutation matrix in this case. So there is a shortcut here, that you should only change the rows of identity matrices, then you would get the desired permutation matrix. How? So the original permutation matrix identity matrix is 1 0 0 1. So to get the exchange rows, you'll have operation like this, and you'll have the operation like this, and if you do this operation, so 0 1 1 0, so if you multiply this matrix with any 2 by 2 matrix in the world, that would exchange the two rows, right? And this is true for this permutation matrix as well. So this is the original permutation matrix 1 0 0 1, and we want to exchange the columns, right? So that would give me this output 0 1 1 0. So that's, so the columns are exchanged here. So this is the desired permutation matrix. So if you want to do any permutation on any sort of matrix, just replicate the operation on the identity matrix and you'll get the desired permutation matrix. Okay, so let's have so this is the concept of permutation matrices. Okay, now let's talk a little about the inverse matrices. Okay, so if you remember from the previous lecture, that what was our E21. So our E21 was we multiplied three we multiplied 3 with the first row, and we subtracted it from the second row to get a 0 in the 2 1 position, right? So our E21 should be 1 0 0 minus 3 1 0 0 0 1. So now you want to get a matrix that undoes this operation, right? So suppose you have got, so after multiplying this matrix you got 0 at the 2 1 position, so you want to undo this operation, right? So that means you'll get the number back at the 2 1 position. All right, so what operation or what matrix would do that? This is very simple. If you think 1 0 0 minus 3 1 0 0 0 1, so this is, as this is row operation, we'll have to have a multiplication at the left side of the matrix, and that undoes the operation. That means there should be no significant operation done on your considered matrix. That means this is like multiplying the matrix with an identity matrix, right? So there should be something here that undoes the operation that this matrix does, and you'll get the identity matrix. That means a neutral operation. All right, so what should be the matrix here? So this is very simple. If you use your intuition, you will know that as we have multiplied 3 times multiply 3 with the first row and subtracted it from the second row, we will have to add that 3 with the first row and multiply 3 with that first row and add it with the second row, right? So that would actually do the trick. So 1 0 0 0 0 sorry 0 0 1. Okay, so this matrix here actually does the operation of this matrix. So if any matrix undoes the operation of another matrix, so let's say A, there is a matrix A that does some linear transformation on any space. So if there is another matrix B that undoes the operation that this matrix does, so B is the like antidote of A, then B is called the inverse of A. Okay, so B is called the inverse of A. So that's where the idea of inverse matrices come from. Okay, but not if we talk about inverses. If we talk about inverses, so inverse matrices are only for square matrix. Okay, so not all the matrices are invertible, you already know that. If it is invertible, then there is some matrix. So let's say you have a matrix A. If this is square and this is invertible, then there should be some matrix A inverse that has the following property: A into A inverse equals to identity matrix. That means they undoes the operation of each other, and this is also true for this A inverse A equals to I. So if a matrix has an inverse, then you can call that matrix a non-singular matrix or an invertible matrix. But if doesn't have it, it is called singular or in a non-invertible matrix. Okay, so let's talk a bit about the singular or non-invertible matrices. So let's say you have a matrix A equals to 1 2 3 6. So from the high school level, you know that this matrix is not invertible. Why? The simplest answer is the determinant here. The determinant here, I think I did a spelling mistake here. Yeah, the determinant here is 0. So you multiply this corner and you subtract it from the corner AD minus BC for any matrix ABCD, and this is 1 into 6 minus 2 into 3, which is 0 in this case. Yeah. So now, as we are talking about the determinant, we have to know a bit about the determinants. Okay, so recall on the concept of linear transformation. So if you think from the perspective of linear transformation, you already know by this point that a matrix does a linear transformation, and it basically, when a matrix does a linear transformation, it basically stretches or squeezes the space, right? So that was if we have a matrix 1 5 3 7, then the transformed I cap lands on, let me clear the canvas. Yeah, so the matrix was 1 5 3 7. So if you have this matrix, this basically says that the transformed I cap actually lands on 1 5 and transformed J cap lands on 3 7. So this does some stretching or squeezing on this space. Okay, so one thing that's pretty useful to understand this transformation is how much it stretches or squeezes the space. Okay, so more specifically, finding the factor by which the previous area is increased or decreased. All right, so let's say for the previous, like before the transformation, one or area of anything or area of any object is like this A. Okay, then after the transformation, the transformed I cap actually lands here, and transformed J cap lands here. So there is some stretching, as you can see. Okay, and this object here has transformed into this. Okay, let's say it is transformed or stretched by a factor of C. Okay, so for example, let me give you a more specific example. Think about this matrix 3 0 0 2. Okay, so let's say before the transformation we had this I cap, we have this J cap. So this was the area, which is 1 square unit, but after the transformation, the transformed I cap lands here. This is 3 0, and transformed J cap lands here 2 0. Oh, sorry, 0 2. Now the area bounded by this transformed I cap and J cap, as you can see, is stretched or scaled or increased by a factor of 6. Okay, 2 into 3, this is 3 and this is 2, this is 6. Okay, so now this spatial scaling factor right here, this 6 C in this case that I introduced, is C. This spatial scaling factor, the factor by which a linear transformation changes any area, is called the determinant of the transformation. Okay, so by the determinant, if I tell you that the determinant of this matrix is 2, so you'll have to have an idea in your head that if I do any linear transformation by this matrix which has a determinant of 2, then after the transformation the area will be increased or scaled by a factor of 2, or their area would be doubled. Okay, so what about the decimal points? Let's say if I give you a matrix with a determinant of 0.5, what does that mean? It means that the area is squeezed, right? The area is squeezed into a space where any object after the transformation has been half of the size of the previous state of transformation, right? So if the determinant of any transformation, let's say for example 4 to 2 1 is 0, as you can see the determinant is 0. So what does that mean? It means that it squeezes all the space onto a line. Okay, so maybe this area, as you can see, this I'm talking about this example. So let's say after the transformation it will have, so the transformed I cap and j cap falls on the same line, and it will have this shape will have a transformation like this, like the red line here. So as we know that the line occupies no area, so the determinant here is 0. Determinant also allows negative values. Okay, so this has to do with the idea of orientation. Okay, for example, let's say so this is the normal case, and this is the x-axis and this is the y-axis. So if after the transformation this it flips, the orientation flips, so let's say this goes here and this comes right here, the y-axis comes right here, then you'll have this. So this is x and this is y. So this kind of transformation, so the matrix that does this transformation will have a negative determinant because it has changed the orientation of every space on this space. Okay, this is say for example flipping a paper on the other side. Okay, if you flip a paper on the other side, you'll have the orientation changed of every object staying on that paper. Okay, so in that case the determinant would be negative. So what about, so far we have talked about the 2D cases. What about the 3D cases? So what about 3D cases? A, B, C, D, F, G, H, I. So what about these 3 by 3 matrices? So simple, for 2 by 3 matrices the area was stretched or squeezed. In case of 3 by 3 matrices, the volume would be the volume actually gets scaled, it is stretches or is squeezed. Okay, so the same theory or same concept or idea of negative determinant and zero determinant goes for 3D space as well. Okay, so in case of negative determinant in the 3D space, the orientation is actually measured by the Fleming's right hand rule, if I can remember correctly. Okay, so if I give you any matrix, like let's say our previous matrix that we were working with, 1 2 3 6, then what can you say about this matrix, or what linear transformation is done by this matrix? You can now interpret this from the perspective of determinant, I hope. Okay, so for inverses, whatever linear transformation a matrix A does, so let's get back to our previous concept that we are talking about, which is the inverses. Okay, so for inverses, whatever linear transformation a matrix A does, a linear transformation. So for inverses, A inverse does the opposite linear transformation. Okay, so it actually take the space to its previous form. So let's say you have done this from this space to this space, you have done this transformation by a matrix A. So by A inverse, you can actually go back to your previous form or previous space. Okay, so this is what inverse matrices are for. So a matrix with a zero determinant squeezes the space into a line, so inverses cannot take back to its previous shape, right? So if you have any matrix A that has determinant 0, I told you that in this case, like in this case, it squeezes the whole plane or space into a single line. Then inverse cannot take it back to its previous shape because it cannot make anything out of 0, right? So that's why they do not have any inverses. Okay, so this is the reason why an non-invertible matrix, a matrix with a zero determinant cannot have an inverse of it. Okay, so, or in other words, I can say that matrices with zero determinants are non-invertible or singular. Okay, so we'll take a different matrix. Let's say we're working with this matrix 1 2 3 7. As you can see, this matrix is not non-invertible. That means it is invertible surely. So its inverse form should be this A inverse equals to I. Okay, so you can also do the operation like A inverse equals to I. That in that case we have to do the row operation, but we're interested in the column operation. So I have this matrix 1 2 3 7. I have its inverse A B C D, and by multiplying these two I get the identity matrix. So from the concept of linear combination of matrix vector multiplication, we know that if we from these two I get 1 2 3 7, then A okay, I want to change something here. Let's say this is B, this is D. Okay, this is just for the ease of calculation. Okay, I could use the same same letters, no worries. So I know that this into the first column, so column matrix into column gives me the first column here 1 0 and 1 2 3 7, into the second column CD gives me the second column of this matrix 0 1, right? So how can I do it actually? How can I solve for A and B? For the first let's say this is equation 1 and this is equation 2. So what should be the solution? How can we find the solution of A, B and CD? So we actually showed you a solution method in the previous lecture, that is the Gauss-Jordan elimination. Okay, for example, I will solve the two equations here at once. Okay, how? So this is my matrix 1 2 3 7. I want to augment it with the solution, which is the identity matrix, or the right hand side. If you could remember, the augmentation matrix was A B, A connected with B. So that's what I have done here. So I have to get a 0 here, okay, and I'll have to get a 1 here, okay. So if we do the operation, if I multiply if I multiply 3 times row 1, 3 times row 1, so row 2 is row 2 minus row 1 into 3, so I'll get 1 2 0 1, okay. And for this one I'll get 1 0, then a negative 2 and a 1 here. Yeah, this is okay. Now as you can see, we have this matrix, the augmented matrix. Now for getting the A inverse, you have to do the upward elimination. So this is one extra step for getting the I'll tell you the essence behind this, but just for the time being, know that you have to do some upward elimination so that to get I at the left side. That means in this side you want to get the I, or the identity matrix. Okay, so if you multiply this pivot by 2 and subtract it from this one, you get it, I guess. So 1 0 0 1, then you'll get 1 5 here, -2 here, -2 here, and a 1 here. There might be some mistake in calculation. I hope not. Okay, so what you have got here is that you've got the I here, right? So the essence behind this is we started with A concatenated with I, and we have got at the right hand side the I concatenated with A inverse. So this is our A inverse, and there was some elimination process here, right? So if we just drew the if we just do the multiplication here, it is EA. I cannot do the multiplication, I guess. Yeah, this is okay. So so first you started off with the matrix A, then you concatenate with the I, then the goal is to get the I at the left side in this position, so that you get the inverse of A at this position. Okay, so this is the method of getting inverse of any matrix by the approach of Gauss-Jordan elimination. Okay, so I hope this is clear. So if you have any question, we can discuss it more in our discussion class, inshallah. Yeah, so to the next class. Assalamu alaikum. See you in the next class, inshallah.